Hello. This lesson is about modeling. You can kind of think of it as the second part of our measurement and uncertainty class. You have good data, now what do you do with it? In a very real way, all of science is modeling. Science is in simulacrum, as they say in pretentious Latin, meaning it is an approximation of real life. Now, I'm not trying to shake your foundations here. What do you mean science is only an approximation? Well, let me give you an example. Say you have a cannonball that you're firing out of a cannon, and you want to know where it goes. Well, projectile motion, 2 equations, nice and easy. Unless there's air drag. Okay. And if the ball spins at all, then there's Magnus force. And there might be wind. And wind and air drag are both going to be affected by air density, which is a function of temperature and humidity and altitude. For that matter, gravity changes as a function of altitude and underlying geology. One of the ways that we can find things like oil and metal deposits underground is by looking for changes in local gravity. And I guess all of that drag is probably going to heat up the ball, but maybe not as hot as the initial explosion. So there's going to be some change in temperature, which is all going to change the size of the ball and its resistance in the air, and there could be some thermal currents, and very quickly you understand that real life is so much more complicated than we ever write a story problem to be. But 3 equations, projectile motion and drag, will get you accuracy to within a couple inches most of the time. So that's fine. That's the approximation that we are comfortable using. The first step in making a model is pattern recognition. And luckily, we as humans are so good at pattern recognition. We are so good that we will see faces in doors and grilled cheese sandwiches, and we have superstitions. I wore those socks, the team won. I wear the socks again, the sports ball team won again, therefore, lucky socks. That's pattern recognition. From an evolutionary standpoint, it's good that we're too good at this, because it is much better to think you see a lion when you don't than to be the one who didn't see the lion. So this pattern recognition is hardwired into our brains, something we're very good at. But recognizing a pattern isn't enough. If you see a pattern, you can make a prediction, usually from it, right? A, B, A, B, A. Sure. But a prediction without an explanation is a party trick. And the other side of that is almost worse. An explanation that doesn't predict anything is just a story. In ancient Greece, there was an astronomer named Ptolemy. If you know your ancient Greece, that could be confusing. There are like 6 guys named Ptolemy. The astronomer Ptolemy developed a thing called the Ptolemaic universe. This was a geocentric model where the Earth is stationary and everything rotates around it. But by his explanation, everything needed to be moving in a circle at a constant rate. But if you look at the stars and the planets, that doesn't happen. So what he did was he designed these epicycles where the Earth is stationary, and then around it there's a circle, and on that circle is Mars, but not directly on that circle. On a point on that circle is a circle, and Mars is on that circle. And for things that were particularly bad, like Mercury, you had a circle mounted on a circle mounted on a circle, and each of those was moving at a constant rate. That was a pattern that worked. You could, with that system from ancient Greece, accurately predict the sky for the next 1,000 years. But there's no reason it should work that way beyond that's the pattern. You've seen the pattern and that's what it is. He had a pattern without a good explanation. Now, to see an explanation that doesn't predict anything, you can pick any pseudoscience, chicanery explanation of the universe with other worlds and fairy circles that, unless you specifically have read that one book, produces a universe that is functionally identical to the one the rest of us live in. You have an explanation that doesn't help. That's a fairy tale. So how do we find a good model? Well, first, you need a good set of data. Let's take a look at an example here. Based on this data set, what shape do you expect the data to take? Is this a line? Is this a curve? Is this a parabola? Okay, now look at this data set. Again, what kind of trend are you expecting here? Is this perfectly straight data? Is this a straight line with one outlier? Okay, how about this one? Let's look at this data set. Is it clear to you how this data should look? Now, how many of you noticed the axes on these data sets? Look at those units. Look at how these are scaled. If we directly compare these three data sets, we can see whatever conclusions you thought you had, it's pretty clear what the actual data looks like now that we have a good set of data. If we look at too small of an area, or we look at a big enough area but not in enough detail, we can't see the pattern. So this is really part of, we need a good set of data to start with. So you have your data. It's good, we trust it, you can clearly see trends in it. Now you need to figure out how that trend looks mathematically, and if it's a good fit. Well, there are ways to see if your data fits: RMSE values, regressions, R-squared values, things like this. But the single most important thing is, does it make physical sense? And to do that, we need to look at the physics, not at the math. You can put almost any data you want in a graph and fit it with a 12th order polynomial. If you give me a high enough order polynomial, I can make the Philadelphia skyline. Doesn't mean it's good. We need to look at what that math actually means from a physics perspective. Let's look at an equation you already know. So we see a lot of letters here, we see a lot of numbers. Let's go ahead and strip it down to just its polynomial form. Now, looking at these values, something that I hope you can see, when we look at the polynomials, we have these coefficients. And if we compare the coefficients to the physics equation, each of those coefficients is a value we can also measure empirically. We can measure the starting position. We can measure the starting velocity. We can measure 1/2 the acceleration. That's how we know that this equation makes sense physically. Every coefficient in it is something we could measure independently. It is possible that the data you've collected, due to whatever reason, is better fit by a 5th order polynomial as opposed to a third order polynomial. But can you measure what all those values should be? Do you know what all of those coefficients are? If you don't, maybe you're overfitting. What is overfitting? Overfitting is when you let the computer have too many knobs. If you give it a 7th order polynomial, it has 7 different coefficients that it can tweak and do whatever chicanery it wants to try to get the line to go through the dots. Because your computer doesn't know physics. It only knows connect the dots. So it can give you values that make no sense for being in the real world, because it doesn't know that. It just connects the dots. Beyond not knowing physics, the other thing that curve fitting is really bad at is exponents. Let me give you an example. Look at this curve. Is this an x squared curve? Is this an x to the 4th curve? Is this an x to the 8th curve? What is curve fitting good at? Well, curve fitting is very good at finding those exponents, and it's great at averagings. So that's really what we're doing when we're taking a slope. Sure, you could take your data point 1, calculate a value. 2, calculate a value. 3, calculate a value. Calculate all of those values, average them, you have your thing. But what if some of them are bad? What if some of them aren't good? They're in the averages as much as everything else. But if you graph them all and you take a slope, now you have a weighted average across all of your data. Outliers look like outliers, and you can get very precise calculations by taking a slope. Also, we as humans are very good at looking at shapes. We are not good at reading data tables. So it's often much, much easier to see a graph and understand what's going on and get insight into behavior than to look at a data table and try to find a trend. As I've said, the big problem with the computer trying to fit your physics data is that it doesn't know physics. But you know physics, or at least enough physics to help the computer along. So let's take a look at this equation. Right? This might be a thing that you play with. Maybe it's Hooke's law, maybe it's something else. But this equation makes some assumptions. What are they? Well, the two real big ones are that your value of x is perfect, but maybe it's not. We took this data, there could be some systematic error. Second, what is the value when x equals 0? That's right. But what if at x equals 0, y doesn't equal 0? What if there's some displacement there? What if there's some offset? If there's any amount of offset, and if x is at all not right, the computer is going to read this, and it's going to hate you, and it's going to put out garbage. But we know that these are problems, so we can fix them by instead using this equation. Now, what did we change here? Well, we added 2 fitting parameters. The first is that we've added this additional x term, right? That we now have x plus b. What is that plus b? That plus b is whatever we know to be the change in x. Maybe there's a calibration error there. Maybe we know that, maybe we just don't trust our sensors. And we know there could be an error. If our data is perfect, b could be 0 in our fit, and we'll be really proud of ourselves. But maybe it's not, and we can address that. The other one is that c at the end. That's our offset, our background, right? What if there's, whatever this y is, what if there's always some of it present? That is now there in the c, and we can account for that. Another way that you could help the computer is by taking your equation that's difficult and making it into an equation That's less difficult for the computer. Because what do we know that computers are not great at? Curves. But what are computers good at? Straight lines. Straight lines are easy. They're so easy that your accounting software can do them. That's right, Excel is accounting software. So how do we make this into a straight line? Well, we could do something like this. Now, this value we're trying to get out isn't buried in a fraction, it's the slope. And finding the slope of data is easy. But we, as the physicists, had to make that an easy thing to find by rearranging this for the computer. If we want to go even further with this, we could use linearizing and fitting parameters to double check empirical measurements. So let's go back an equation and we'll start with this one. What if we want the computer to verify B and C for us? We have empirical values, but we're not sure if those are right. Well, what we can do in that case is pretty straightforward. We know what they are, we let the computer fit it, and we compare their values with our values. Great. What if we don't trust this equation? Like that exponent. What if we don't know if that's a 2? What if it could be a 3? What if it could be a 1? What if it could be a -1/2? Well, we know computers are bad at exponents, so we can't let it fit the exponent, but they're good at slopes. So how do you turn a slope into an exponent? That's right, the thing you never thought was actually going to be useful, logarithms. So if we take the log of both sides of this equation and then do a little bit of algebra to it, we get this. Now, if you look here, that exponent is now the slope. Caveat, very important here. In this fit, where do we get those values for B and C? We must use the empirical values that we measured by hand. Why can't we use the values that the computer gave us in that first fit? Because the computer will perform any sin necessary to get B and C to produce the exponent we gave it. So if we found B and C using an exponent of 2, it will perform anything necessary to guarantee the exponent's 2. So if we use those values to check the exponent, they're going to be 2, because that's what it was designed to do. So if we do this method, we must use empirical values that we have measured independently to verify that exponent. If there is one lesson that I want you to take away from this video, is that curve fitting is never a replacement for physics. You should never fit your data to try to figure out a theory. You verify a theory by fitting your data. The reason that this is so important is because data is never going to be as clean or as pretty as you hope or as it could be. And there is always going to be some room for error in what this could look like if we squint hard enough. So you can never look at your data and squint until you see a line and assume that that line is correct. Think back to that example we did of the 3 different graphs. If you squinted at the wrong one of those, your theory's gone. So you must always have a reason, an underlying physics that demands that this is the math we use. To really drive that point home to you, we have a project. that we're going to talk about today and you're going to work on next week, where your group is going to get a phenomenon and you are going to have to model that phenomenon. For a lot of these, the modeling part is pretty straightforward. The equations make sense. You can find them easily. That's not the project. The project is, can you come up with a physics explanation why that mathematical model is the only mathematical model that makes sense? If you say, this is an exponential decay because if you look at the equation, it's exponential and it decays. That tells me nothing. That's a tautology. If you tell me this is what's happening inside this device, and the only way to explain this behavior mathematically is exponential, now we're talking physics. So that's what this project is going to be. You are going to study a phenomenon with your group, figure out what model fits it, and explain using physics, not math, physics, why that is the only math that makes sense. I know that sounds like a big project. We are going to talk about it. There's going to be a lot of time devoted to this. I promise it's not nearly as scary as my gravitas just made it sound. So, I think this is actually going to be a lot of fun once you get to it. I hope all of this insight into modeling, made sense and it showed you a bit of that thought process. And once again, thank you for watching. Let's do that for a third time with the mic on now. No, hello. No. Huh. Wind up and go. Pretentious. Model. Modeling. Model. Why doesn't that fit? Model. Lesson. No, that's. Hey, what's up?
Didn't want to interrupt if you're recording.
Yes, I am recording, but that's fine. You can slide through. There are too many people in my house. That's what's going on right now.